In VLSI, there are two kinds of chips. One is ASIC, the other one is FPGA. Let's look at FPGA, Field Programmable Gate Arrays. It's a programmable chip. I would say a ready-made chip. We can buy this chip from the vendor. There are vendors like Xilinx and Altera, and you can create your own design. Later on, you can download your design into the chip. This is how it works. The chip is empty. You can download any kind of design. You can erase it. You can reprogram it. It's a programmable chip. So it's beautiful. You can do a lot of experiments. For example, while doing the design, something goes wrong, then you can erase the design. You can fix the bug. You can reprogram the chip. This is used primarily in defense sector because there we don't expect too much of customization. Also, FPGAs are good for certain applications like mathematical intensive calculations. You know, the companies like Xilinx and Altera, they also claim that they include a lot of macro cells or macro IPs as part of the chip, and they can do the mathematical intensive calculations efficiently, so you get more performance. When it comes to space related applications, basically mathematical calculation is critical. That's where FPGAs have been used extensively. There are constraints. For example, you want to realize a complex chip like A11, FPGA might not be able to support because it doesn't have the enough space. You can think of realizing complex designs in terms of million gates, not in terms of billion gates. So obviously we need to think about ASIC. Look at ASIC, application specific integrated circuit. Now, one requirement is very obvious. We want to customize the area and power. The chip doesn't have to be complex. Even it can be a very simple chip. For example, I want to design chip something similar to this button. I would like to have chip on my blazer. The chip should be able to get all the information, my body temperature, heartbeat, and it should be able to transfer the information to my mobile phone, and then mobile phone should be able to process the information. So here you look at this, the size is critical. At the same time, power consumption. If it consumes more power, obviously I need to think of including a battery unit. Then nobody's going to buy the phone. Even women can also think of having this kind of chip as earring. Then the chip should be able to generate power from the photons. Now there are some LED lights, they emit photons. It should be able to generate power from the photons. So here the power consumption is very critical. That's why if you look at the chips which have been used in toys, they consume very low power. Though they are not complex, still power consumption is critical. At the same time, when it comes to designing the complex chip like A11, multi-billion complex chip, then obviously we need to go for application-specific integrated circuit because the size is important. So when it comes to designing the mobile chips or iPod chips or iPad chips or the chips for the laptops, obviously we go for ASIC. And ASIC, there are some risk factors. ASIC respins, very expensive one. At the later stage, maybe during back-end flow, if you find any functional bugs, basically you have to start from the beginning. You have to look at like how this can be fixed at the architecture level. If you do some modifications in the architecture, you have to rewrite the code. You have to simulate it again. You have to synthesize it again. It's kind of iterative process, and that's going to consume a lot of time. So that's very expensive. That's why verification becomes critical for ASIC. After creating the architecture, you have to look at how best you can verify the source code. And we have to find the bugs as much as possible during simulation phase. If you leave any bugs, later on, it would be more expensive. That's called ASIC respin. So what we do is sometimes we think how we can use FPGAs to verify ASIC. Look at FPGA, the last one. FPGA prototyping for ASIC verification. Obviously, everyone goes for simulation. You have written the RTL code, and then now you need to write test bench. You have to generate stimulus. You have to verify the functionality. But the simulation is simulation. We don't gain much confidence. So what we do is we try to do this verification on the actual hardware. So we create the prototype for the chip. Now you think of A11. It's pretty complex. more than 4 billion transistors. So one FPGA might not be enough. We might need multiple FPGAs, like 10 FPGAs or 20 FPGAs. And then what we do is we partition the chip A11 into multiple major hardware blocks. And then we try to map each block onto each FPGA. Then we put all the FPGAs together on the board, and the entire board will be equivalent to A11 chip. This is called FPGA prototyping. Here, the only difference is it might not run at the same frequency. The frequency might be low, but still you can verify the functionality. So what I'm trying to do is I'm trying to generate a lot of real-time scenarios, and I'm trying to verify my design on the actual hardware. Even I would be able to connect a lot of peripherals, the real-time peripheral devices with my chip, and I would be able to do a lot of experiments. And this gives me confidence. I can fix bugs even in the software also. This is called FPGA prototyping. That's where FPGAs have been used extensively. All right. In this video, we discussed about VLSI, what is VLSI, and how we design powerful electronic devices like smartphone. We discussed pretty much about mobile SoC architecture, and then we discussed about Moore's law. We also discussed about FPGAs and ASIC. Hope you enjoyed this video. Thank you.